Welcome to a session on number system. We have already begun with the session and have understood about some rational numbers and how to locate rational numbers between two given rational numbers. Now we move on to irrational numbers, the numbers which are not rational, the numbers which cannot be expressed in the form which is P by Q. Those numbers are like the ones I say root 2. There are many such as actually root 3, root 5, which cannot be expressed in that form, and so on. There will be many as such. How do we locate these kind of irrational numbers on the number line? That's what we are looking for in this session, and move forward. The first one I take and help us ourselves understand is we will be locating root 2 and the next one we take is root 3 on the number line. I can just explain how to go for it. Might not be an accurate figure for it. Let us now first make out how root 2 is arrived at. Root 2 might have been arrived at like 1 square plus 1 square. Now in a right triangle, if I can make these two, one of these will be the perpendicular, the other one being the base. This can then be made as the hypotenuse. So draw the number line first. I'll make mark for 0 and maybe this is 1, this is 2 and 3. The first one we need to do, let me use some other color. This is 1, so I draw this to be 1. This is 1 more, so I go up by 1 unit. And I told you the hypotenuse becomes root 2. So this one is root 2 representation, but we need to draw it. Let me mark them. And this as O, that is O, let it be. This be B, that be A, that be B. So we are representing OB as root 2, but that needs to be represented here some on the number line. So this is root 2, that is OB, but we have to place it on the number line. So what we do is, using our compass, mark OB and keep your needle at the point O of the compass. Try to make an arc. I will be using my free hand to draw that. Kind of it might just look. You'll draw an arc taking OB as the radius that might intersect the number line at the point, whatever we name it, maybe M. Then this OM would represent root 2 on the number line. That's not much difficult to draw, but the moment you get any irrational number to draw on the number line, you need to first locate which combination, how many units on the right would help you get that irrational number on the number line. Let us try to locate root 3 on the number line. To locate this, let's also take up the same figure as I had taken the previous one for root 2. We have already got a root 2. Now how root 3 is arrived at? Root 3 can be done as root 2 whole square, that gives you 2, plus 1 square, that gives you 1, that is 3 root over. So this gives you the root 3. So root 2 square plus 1. Now what we do is, from this point, that is B, from this point B, draw a 1 unit, this one. So I'll draw a 1 unit here, It should be 90° 1 unit, because we are taking again root 3 becomes our hypotenuse, and we will try to make one side to be root 2, the other one being 1. So we have already got our root 2, which is the base, and I'm taking 1 as this 1 unit, and I name this point supposedly D. We get it as D. Now once I join this point OD, now OD will be representing root 3. This is 1 unit BD, because I explained how root 3 is arrived at. It is root 2 square plus 1 square, so this is root 3. We'll follow the same method as we did in the previous one. So to draw that on the number line, you have to draw an arc with OD as the radius, so that would just be here. Maybe this point beside M, which I might name as N. So ON is now root 3. So any question which we get has to be first made up how that is arrived at, because we are every time applying a Pythagoras theorem to get that irrational number on the number line. We now take up to represent root 5 on the number line. Sorry. Root 5 can be arrived at as 2 square plus 1 square, because that's giving us 4 and it's 1, so root 5 square. Sorry, root over of 5. I'm just taking up another number line to have a clear view of it. This is O and 0 as well. This is 1, this is 2, and this becomes 3. So this is 2, and I'll take 1 here. So, and I join O to this point. Maybe I name this as I did in the previous one, this being A, this being A, that's B. So in this figure now, OB is representing root 5. So you have to take your radius as OB, draw an arc. It will be somewhat between 2 and 3. My figure again is not accurate. So this point, once you draw the arc, the point which intersects the number line, maybe I name again this as M. This OM is now representing root 5. Let us now move on with decimal representation or decimal expansions. We'll come across when there are numbers which are in a fraction, like 10 upon 3. There is suppose 7 upon 8, and there is also 1 upon 7. If we try to solve all this fraction representation, we would find that they are all not similar. If I divide 10 by 3, you see I'll get a decimal here, and I will be getting 3 again gives me a 9, that's 1, again a 10, that's 3, and it continues. That means it is not getting terminated, and 3 is getting repeated every time I divide it. I take the next one, which is 7 by 8. Zero get a decimal, it is 8. 8 is 64. That gives 6. Again I get a decimal, then it is 7. 8 is 56. I left with a 4. Oh, it's getting terminated. That means the remainder becomes 0 at a certain stage where I got 0.875. Now I take up 1 upon 7, dividing 1 by 7. So I get 0, 1 is 7. I'm getting a 3. I continue the simple division. So it is 4 7s are 28, and then 2 7s are 14, 6 8s are 56. I have already got 4 numbers after decimal, 4 digits after decimal, but it hasn't terminated yet. It is also not repeating as in the first case. In the first one we got 3 repeated, second one it got terminated, and if you see here, it is not getting terminated and it's not even repeating. So there are 3 different cases we have come across. 49, and it will actually be getting continued because I already have reached 1. So what do we see? The remainder either becomes a 0, the remainder never becomes a 0, and even if it is not becoming 0, it is either getting repeated, a 1 digit is getting repeated, or in this case, like as I have already reached a 10, that means if I continue dividing, I'll be getting 0 1 4 2 8 5 7 again as that certain number. So 1 is called terminating. This one is called terminating decimal. Terminating decimal. This is called non-terminating recurring, or it is also termed as repeating. This one is also non-terminating repeating, but both has got a different type of repetition. Here only 3 gets repeated. Here this whole set of 6 digits get repeated. Repeating. So these are 3 different expressions on when you expand any real number, any fraction into decimal. Based on that, we'll proceed into another session where we'll represent or take up questions on these decimal expansions, like how a decimal expansion is represented as a rational number or not. Hope you followed it quite well. Thank you.